All right, hi everybody. Here's question 121 from chapter 6. This question is another thermal equilibrium problem. This one with 3 variables instead of 2, as per question 67. We're not given the masses of these cubes directly, of the aluminum and the copper one that are both submerged, but we can calculate the masses with table values. Okay, so what we're going to do is find the mass of copper that's present first. Okay, that is going to be equal to the volume times the density. Volume is going to be our edge length of the cube cubed. So we had 1.55 centimeters, which we're going to cube. And we're going to multiply that by the density of copper, which is 8.96. 96 grams per cubic centimeter. So that's going to give us, give me a quick second, 5 cubed times 8.96. So we'll call that 33.367. Sorry, 366. Okay, so there's the mass of copper. All right, mass of aluminum. All right, we'll use the same equation with aluminum value. Okay, the length of the side of the cube here is 1.62. 1.62. Whoops. Times whatever the density was, 2.70 grams per cubic centimeter. All right, and that is 11.479 grams. Okay, there's 2 down. I'm just going to double check that one. I did that a bit fast. Times 2.7. Yep, that is it. Okay, last is the water. All right. We're going to use the same. So this, I believe the volume that these were submerged in was 100 milliliters. That's correct. And we got 0.9, so this is going to be 100 milliliters. And the density was given in the question as 0.998. 98 grams per milliliter. So we got 99.8 grams of H2O present. Okay, so there's our masses for all the different species. Just give me a quick second here. 366 and now it's 1.479. Just writing these down because they're going to end up being erased. I'm going to need the space. Okay. So now that we've got those things, there's also, well, the heat capacity values we can look up in the tables later when we do need it. So the important part of the setup of this question is that the copper and the aluminum are both heated to the same initial temperature before they go in, and that simplifies our setup for the problem. We are still going to have like the mass times the heat capacity of aluminum, right? Times like T2 minus T, well, in this case it's going to be T1, right? Because these are the same. Plus the same for copper. It's T2 minus T1 equals the negative. We'll put water as a negative in this one. So the heat capacity of H2O times T2 minus the temperature of the water. So the water did have its own temperature in this case. All right, so then over here, we're going to put these two, we're going to put all these things together. So I'm going to leave these things like that. I'm going to wait until the last minute to start sticking numbers in these things because it's going to turn this into a mess. Okay, so then T2 minus, minus T1. We'll keep that the same. All right, and then that's equal to the same over here. We're not going to bother rewriting that. So then what we're going to do is we're going to start isolating T2s. Right, that's really what we want is all the T2s over here. So we'll do this in stages. So there's that. And that T2. Okay, and then this by H2O we're going to bring out on its own. So we're going to go MCH2O times the temperature of H2O. Right? This is to separate out our T2. And this is then going to be negative because we had a negative before this. So this is going to be negative MC H2O T2. So, and then this is, oh yeah, and then because this was a minus over here for the T1, we're adding, we are adding this whole disaster with T1. Okay, so that is mass and capacity of aluminum plus mass and capacity of copper times the T1 over there. Okay, so now we're going to shuffle the T2 water over here, which is going to be a third figure added. All right. So we have mass of aluminum plus mass and capacity of copper plus mass and capacity of water. All right. Oh, whoops. There shouldn't be equal signs there. Sorry, excuse me. Yeah, let's rewrite this bit right here. That is just T2. Okay, and that is equal to this other stuff here. So this is MCH2O, TH2O, plus all these things, MCAL, plus MCCU times T1. Nearly there. Whoops, I forgot the brackets here. But okay, so then T2 is going to be equal to this divided by this. And we finally have something we can stick all the numbers in. All right, so let's start doing exactly that. So mass times the heat capacity. So I'm gonna be calculating this as I go here. So we had how much mass of the water? 99.8 times 4.184 joules per gram degrees Celsius. Right, and I'm going to multiply that by the initial temperature of the water, which was 22.2 degrees Celsius. So this first term here is 69.9 degrees Celsius plus, this one's going to be a little bit longer. Okay, so aluminum is first. So 11.479 times heat capacity is 1.5746. All right, and that is times oh, whoops, hang on, sorry, that's not the right value. 11.479 times 0.903. Yeah, that's the mass times heat capacity. Okay, perfect. Okay. Plus, I got to do the same for copper. It's just 33.366 times 0.385 for copper. All right, and we're multiplying both those things by the temperature that they went in at, which was 55 degrees Celsius. Okay, so these terms over here are 276.6, and we're dividing those by all these things here. So, if I divide this by 55, it's that, and then I'm adding to that the mass of the water times its heat capacity, which was 4.184. All right, so we divide this by 440.8. Right, this here was also degrees Celsius. Sorry. Okay. Let's see what we get. 269.9 plus 276.6 440.8 equals 23.9 degrees Celsius. There you go. There's your answer.